Let's take a look at zero-order reactions involved in drug degradation. These are going to be the same principles that we'll look at next semester with drug elimination in pharmacokinetics. So with zero-order reactions, the amount of drug that's lost is going to be independent of the amount of drug that's present. This means that the fraction of drug that's lost over time is going to increase as the amount of drug present decreases. Finally, we'll see that a plot of drug, either amount in the case of drug degradation or concentration in the case of drug elimination, versus time is going to be linear. So if we take a look at an example of zero-order elimination, we see that in the time after drug administration column that the interval we're looking at remains constant, so we're looking at 1 hour intervals here. The second column has the amount of drug that's going to be present in the body in milligrams, and if we take a look at the amount of drug that's eliminated each hour, what you'll notice is that the amount of drug that's eliminated each hour remains the same. So each hour we're losing 150 milligrams. So in this case, our K, our zero-order rate constant, would be equal to that 150 milligrams per hour. So if we're losing 150 milligrams of drug each hour, that means that the fraction of drug that we're eliminating over time is going to change. So in this case, the fraction that we're eliminating each hour is going to increase. And what we're talking about here is that in the first hour, we lost 150 milligrams from that 1,000 milligrams that we started with. So we only lost 15% of what we had. So for our fraction there would be 0.15. In the second hour, we lose that same amount. So we're still losing 150 milligrams of drug. However, since we only started with 850 milligrams, that means that we're going to be losing a larger fraction or larger percentage. In this example, it would be 18% or a fraction of 0.18. And so as you look down, then the column fraction of drug eliminated per over preceding hour, you can see that that does increase as the amount of drug that's present in the body, or that's just present in the case if you're looking at drug degradation, as that amount decreases, your fraction eliminated will increase. As I mentioned, if we plot the drug amount versus time, you can see that we get a linear plot with our zero-order degradation. We can fit an equation to the data that we have. And remember, for a linear plot, your y is going to be equal to mx plus b. This just has it rearranged. So we have our y is going to be our amount or concentration at any time is going to be equal to, we'll put our intercept first, so our original concentration C is 0. And then we're going to have our slope. In this case, it's negative. So we have negative k, and then x is our t. So that's how we come to the zero-order equation that we were looking at. C is equal to C0 minus KT. We can then use this equation to solve for what our drug amount or drug concentration will be at any given time. So in this case, if we were interested in what the drug concentration would be, say at 2.5 hours, here we don't have an actual measurement, we could solve for this using the equation we have. So our concentration at that time would be equal to our intercept, or starting concentration of drug, 1,000 milligrams, minus that 150 milligrams we're going to lose per hour. In this case, our time would be 2.5 hours. And so our C is going to be equal to 1,000 minus 375 milligrams, so our C at that time would be equal to 625 milligrams. So as long as you remember that a plot of drug amount or drug concentration versus time is going to be linear for zero-order reactions, you should be able to derive the equation yourself, knowing that you're going to have our y equal to mx plus b. So here our concentration is going to be equal to negative k was our slope. It's negative since we're losing drug over time, times our x, which is time, plus our intercept of C0, our starting concentration. So you can just rearrange that to give you the C is going to be equal to C0 minus KT. In knowing this information, you can solve or derive your equations for half-life and shelf life. With half-life, remember that our concentration is going to be equal to 50% of whatever our original concentration was, so we can say C then is equal to 0.5 times C0. We can then plug this 0.5 times C0 in for C in the original equation, so that means now we're going to have 0.5 times C0 is equal to C0 minus KT, and then we can just rearrange the equation solving for our time. So our time at 50% the concentration, or 1/2, is going to be equal to 0.5 times that original concentration divided by K. Similarly, remember that at the shelf life, the concentration we're using, C is going to be equal to 90% of our original concentration, so C equals 0.9 times C0. We can then again substitute this 0.9 equals C0 in for C into the equation, so that means that 0.9 times C0 is going to be equal to C0 minus KT. And again, we can just rearrange the equation solving for T. So our T90 is going to be equal to 0.1 times the original concentration divided by K. So that pretty much wraps up everything you need to know about the zero-order reactions. Again, if you just remember those 3 bullet points from the first slide where we talk about the fact that with zero-order reactions, we're losing the same amount of drug per time using the same time interval. That meant then that the fraction of drug that we lost over time is going to increase as the amount of drug present decreases. And then lastly, that the plot of drug versus time is going to be linear, and that enables us to recall what our equation is going to be for that linear plot, and we can use that information in order to derive both the half-life and shelf life equations.